Welcome to a lesson with Dr. Powell. In this video, we're going to compute the derivative of f of x is equal to x to the fourth using a limit and the h strategy this time. So we're going to use the h strategy with the limit, and how is that going to work in order to compute the derivative function. So again, we're going to have one point with an x, throw it in x to the fourth. The other point's going to have an x plus h, and then you put an x plus h in here. You're going to x plus h to the fourth power. So this is 1 point, this is the y value of 1 point, this is the y value of the other point. The difference of them rise over run, so we're going to end up getting x plus h to the fourth minus x to the fourth. And the run is x plus h minus x, which is just h. H is always the run. And then we want to take a limit as the run itself is going to 0. Okay, so now if we work with the top, we'll notice that h will actually be a factor of the top, and we can do some division. How do we see that? I mean, we could multiply this whole guy out, distributing a number of times, or we can think about the Pascal's triangle. Pascal's triangle actually gives us the coefficients of powers of this is of a binomial, like two terms added together like this. So for instance, 1 would be like x plus h to the 0 is equal to 1. 1, 1, that refers to, what does this refer to? This is like 1 times x plus 1 times h. That refers to just x plus h to the first power. The next, this triangle works, you can think about it by, you have 1, then a 1, 1, and then how do you get to the next line? You have 1s on the sides, and then you have a 2 right here. So this would be, and then you have an x squared, and the powers of x go down. X squared, x, then nothing. Then on this side you have h squared, h, then nothing. All right, now what is this? This is the result of x plus h squared. But there's a nice pattern going on. So this 1, 2, 1, that actually comes by multiplying x plus h, which I will write with a signify by a 1, 1, where I'm going to think about powers of x, because powers of h are just placeholders for where you don't have a power of x to fill in when you're going up to 2 here. At least on that line here, it's 1. But if I think powers of x, I mean, if I write 1, 1, I could think of it as being 11, or I could think of it as being 1 times 10 plus 1, or I could think of it as being 1 times x plus 1, where it's in base x. Base x representation of that, where I'm just going to ignore the h for now, but I'm still going to get the same coefficients. So you think about it, if I have a 1, 1, and I multiply it by 1, 1, that's going to get me, so it's like x plus h squared. It's going to get me the right coefficient, so 1, 2, 1. Notice it will, if you just think about regular multiplication, 1 times 1, 1 times 1, but just remember, never carry when you add here because we're in base x. We don't know how to group base x. So 1 times 1, 1 times 1, you're going to get 1, 1. Just add down, you get 1, 2, 1. Beautiful. Next line. What do you do? Same thing. Basically, 1 times that whole bit is just 1, 2, 1. 1 times this is just shifted over 1. Why? Because it's like another power of x, and when you multiply power of x, it just shifts the coefficients over. Add down, 1, 3, 3, 1. Do the same thing again, and you're going to get, this 1 times that whole bit is just itself. This 1 times that whole bit is just moved over. So you have what? So 1, 3, 3, 1. And then when you add, and I'm running out of space, but when you add, you'll notice you're going to get 1, 4, 6, 4, 1. Now, you could have gotten those same coefficients simply by thinking about the rule that's what's happening. Because as we're adding down, notice that this 2 plus 1 right here. So this is like plus. Let's keep this straight. That's a multiply. That's a multiply. That's a plus. So when I'm adding this 2 plus 1, or no, it's right here where I'm adding, right? Adding right here. Sorry. 2 plus 1. Really, it's like, so this 1, where was it? It was right here. It's like this 2 plus 1. 2 plus 1 is 3. This 3 came from what? From this 1 plus that 2. So 1 plus 2 is 3. It's like you have a triangle, you're building it. 1, 1, 1, 2, 1. Like I added those two guys to get the 2. 1's on the outside. How do I get the other things? 1 plus 2 is 3. 2 plus 1 is 3. How did you get the next line? 1. 1 plus 2 is 4. 6, 4, 1. So really you could quickly get these coefficients. All that work for that. Yeah, well, just wanted to make sure we had a handle on that. So right here we can actually multiply that out. We can know that this is so as we go now, what are the coefficients? The powers of x go down, so we can think, okay, x to the 4th, 4x cubed, 6x squared, 4x, and then a 1, and the powers of h go the opposite way to 4. H to the 4th, h cubed, h squared, h, and then, all right, and then we're just adding. So really, we just multiplied this out completely. Now, if we were distributing and stuff, we might have to combine like terms a number of times to get these coefficients, 4, 6, 4, but here, this is what we have. And then we're subtracting off an x to the 4th. Notice that cancels. This is all over h. So you could factor an h out of the top. 4x cubed plus 6x squared h plus 4x h squared plus h cubed all over h. And we're taking a limit as h approaches 0. Notice those h's cancel. So now we can throw in 0 for h. And when we do, notice that all of this stuff goes away, and we're just left with that guy right there, 4x cubed. So the derivative, this limit is equal to 4x cubed. Now, we could have realized that something like this would be happening, that really the only thing in the binomial expansion, or in this line, that actually has that'll actually survive and only have one power of h in it is right here. So really we only need to concentrate on this one, and remember that the rest of them will have higher powers of h. So when we cancel out just one power of h, there's going to be more powers of h, and when you plug in 0, it's going to go away. So really in your description we could have simplified our work a little bit if we realized that's really what was happening. We could have simply just so if we're explaining our work and our steps here, if we want to use this Pascal's triangle technique, all we're interested in knowing is just the place that we need. We know that x to the 4th is going to be the first guy, so when we multiply this out, we could have written something like this. We know this is going to be x to the 4th, and we know the line is 1, 4, 6, 4, 1, so it's going to be x to the 4th plus, and then we could say, okay, the next one is x cubed h, but with a 4 in front, right? Plus, and then some things with higher powers of h. It's going to be, so everything's going to have, plus things where you could actually factor out an h squared out of it. Because notice, can't you factor an h squared out of all these guys? Yeah, you can factor an h squared out of that, because that's h squared times h. That's h squared times h squared. That's h squared times h. So you could factor an h squared out of stuff, and then you could say, so really this part is just this minus x to the 4th. And then when you divide by h, you could say boom, boom, and then this part right here, if we unadd fractions, the h going that way, but in this way it will cancel, that way, it will cancel with one power, so we'll be left with h times something. Over here, it'll just simply be 4x cubed. And then when we're taking a limit as h goes to 0, of course this guy's going to go away, and we're going to be left with 4x cubed. So if we need to show our work, we could actually have jumped down to something as simple as this if we understand how the Pascal's triangle technique is working with a binomial and a power. Thanks for watching.